Such an enthusiastic crowd. Welcome to the 33rd Annual Florence Bucke Lecture. It's a very special occasion for us because it allows us to give recognition of the achievements of one of our members in the Faculty of Science for excellence in research. The Florence Bucke Prize was made available through an endowment of the late Florence Bucke. He received a BA from University College in 1926 and taught in Fort Erie until 1971. So as part of the estate made available from her endowment to the University of Western Ontario, she asked, in consultation with the Dean of Science, to award the prize to excellence in research, and in particular, to give recognition to something that had a substantial impact in the last 5 years of research conducted by the individual. So the selection committee for the prize consisted of a group of chairs of departments, and this year's winner was a unanimous choice. Congratulations to Gordon Osinski. At this time, I would like to invite the chairs of Earth Sciences, Gerhard Pratt, and the chair of Physics and Astronomy, Shantanu Basu, to introduce Gordon Osinski and describe his past accomplishments. Gerhard.
Thank you, Charmaine, and welcome to everybody. It's a great pleasure and an honor to be able to introduce my colleague and my friend, Gord Osinski, to you this afternoon. Oz holds a PhD from the University of New Brunswick in 2004. Before that, a bachelor's degree from the University of St. Andrews in Scotland, both in geology. After graduating, Dr. Osinski moved to the University of Arizona for a postdoctoral appointment, and in 2007, he was awarded a prestigious CSA Space Science Fellowship, which first brought him to Western as an assistant professor. And in 2010, he became an NSERC Industrial Research Chair at Western, and he's currently an associate professor in earth sciences and in physics and astronomy. Over the past several years, Oz has made several major contributions to science, and he's considered a rising star in the Canadian and international planetary science communities. His main research focus is the investigation of meteorite impact craters and their effects on the origin and evolution of the Earth and of life itself. As outlined in his nomination letter, Oz literally has rewritten the book in impact cratering, co-editing impact cratering processes and products published in late 2013. As we'll hear this afternoon, Oz's research is leading the way in demonstrating that impact events have played an important role throughout Earth's history. And it's a fascinating subject. It's only really in the last few decades that the importance of impacts in Earth's geological history has really been recognized, and Oz, you've played a major role in that recognition. Oz, of course, is jointly appointed to the Department of Earth Sciences, but also to the Department of Physics and Astronomy, so I'll call on Shantanu Basu, Chair of the Department of Physics and Astronomy, to complete this introduction.
Thank you, Gerhard. And I must say, it's very nice to see so many of you here today. Oz is indeed appointed to both departments, which is a fact that speaks to the joint nature of his research, which incorporates all aspects of meteoritic impacts, from their inception as collisions between orbital objects in the solar system to the catastrophic physics of the collisions themselves, and the long-term evolution of these impacts over geological time. Oz's research incorporates a fascinating and diverse range of interests, from impacts and their wide-ranging implications, to models for the origin and the development of hydrothermal activity, to the implications for the evolution of life on Earth and potentially other planets, such as Mars. Oz is known for his creative use of leading-edge instrumentation, from the application of electron microscopy to the involvement in high-resolution planetary imaging of the Earth, Mars, and Venus. He has been responsible for the development of a unifying working hypothesis for the modeling of impact events. In the words of one of his referees for this award nomination, quote, "Oz's observations and measurements are of the highest quality. His observations and interpretations have challenged some widely held tenets in impact science." During his time at Western, Oz has shown significant vision and leadership. He is the current associate editor for the very prestigious journal Meteoritics and Planetary Science. He is one of the driving forces behind the Center for Planetary Science and Exploration, and he's led the creation of the Canadian Lunar Research Network in 2008. He wrote the proposal to NASA that resulted in Canada becoming the first international affiliate member of the NASA Lunar Science Institute. He's also led the creation of the Planetary Sciences Division of the Geological Association of Canada. In summary, Oz is a dynamic and promising leader in our scientific community who spans disciplines and is advancing the frontier of planetary science. With great pleasure, then, I now invite Oz to present this year's Florence Bucke lecture with the intriguing title, "The Beneficial Effects of Meteorite Impact Events." Oz.
Could I actually ask someone to dim the lights at the front, please? So it's an absolute honor to be here today, and thank you for being inside on such a beautiful afternoon. I hope I will do the introductions justice and talk to you what I hope will be a little bit surprising to many of you, which is the beneficial effects of meteorite impacts. If I ask you to close your eyes, or pretend to close your eyes, and imagine a 10-kilometer hunk of rock hurtling towards London, Ontario, you're probably not thinking of benefits at this point in time. Probably thinking of the fastest way to get out of town. And that's generally kind of the widely held view, is that impact events have been destructive throughout geological time. Of course, the extinction of the dinosaurs 65 million years ago being kind of the prime motivator for this interest. And this is actually an artist's rendition of some poor pterodactyls here flying around, and an object about 15 kilometers across striking what is now the Yucatan Peninsula in Mexico. But I don't want to dwell on these destructive events today, but instead want to talk about some of the more positive things. It's actually kind of neat standing here today. I didn't think I'd be standing here after I started here in 2007. And I also think back to my final year in St Andrews in Scotland when this movie came out, Deep Impact, along with Armageddon that summer. And I think even though they weren't the best movies in the world, to say the least, it really brought into the public's mind the kind of potential for large impacts to hit the Earth. This is one of the few kind of plots I'll show today, but just very briefly, on the y-axis is how frequently these impact events occur, and on the x-axis is the energy in TNT, megatons of TNT equivalent. We use that amount because a lot of our knowledge from meteorite impact events actually comes from the nuclear tests of the 1960s and 70s. And so really, without dwelling too long, you can see that even the atomic weapons that were dropped on Japan at the end of the Second World War are a couple of orders of magnitude than one of the small impacts we have on Earth, which is Meteor Crater in Arizona, and kind of Chicxulub, thank you, in Mexico, kind of the so-called Dino Killer. Doesn't happen very often, maybe on the order of once every 100 million years, but it releases so much energy that really the numbers don't do it justice, and they're mind-boggling. However, once every 100 million years, hopefully the geologists in the room are thinking that's pretty frequent when we think about the age of the Earth being 4.5 billion years. So that's quite frequently throughout our history. As we now know, impact events we now believe are common throughout the solar system and throughout the universe. We just need to look up at the moon on a clear night, even without the aid of a telescope, to see that the moon is pockmarked by meteorite impact craters. So literally tens of thousands of objects have struck the moon since it formed. The Earth should look like that too. And so that tells us something. A large part of the moon, Mars, Mercury, and other planetary objects in the solar system have been pockmarked by impact craters since their formation. Of course, the reason the Earth doesn't look the same is because the Earth is geologically active. And actually, we use the number of impacts on planetary bodies to give us a crude estimate of how old the surface of that planet is, and by kind of analogy, how active that planetary object is. So this is a just kind of plain view of map of the Earth, and all the little red dots are meteorite impact craters. So you can ask me questions at the end, or maybe I'll ask the audience questions as to why there's such a proliferation of impacts in North America, Scandinavia, and Australia. But we now know of about 187, I think, as of a couple of weeks ago, impact craters on the surface of the Earth. So it's not tens of thousands, but there are enough here for us to study. And much of the work done actually started off in Canada in the early 1960s and 70s with actually an astronomer, Carlisle Beals, who was then the Dominion Observer of Canada. And he actually really pioneered the study of meteorite impacts in Canada and globally. And one of the reasons is that, well, we have quite a few. We have our very own meteor crater up here in northern Quebec, the Horton structure that I'll talk about, and a very recognizable one, the Manicouagan structure in kind of couple of hundred kilometers north of the north shore of the St. Lawrence, not too far from Montreal. That is one of the few that you can see from space. So, very briefly, I'm just going to give you kind of impact cratering 101 so that you can put the rest of the talk into context. And so, impact craters are unlike any other geological process. It's what attracted me to looking at impact craters in the first place. I still remember the PhD ad that brought me to Canada that was working on impact craters, which I knew nothing about, going to the Arctic, which sounded cool, and working with NASA, which sounded fun. And I've since learned that they really are such an unusual geological process. We tend to work on long time scales, but you could blink and you'd miss the whole formation of one of these things. The reasons for that is that the projectile, whether an asteroid or comet, comes in anything from 10, 15 kilometers a second for an asteroid up to 80 or 90 kilometers a second for a comet. And so again, just pause and think about that, kind of here to Windsor in 2.5 seconds. That's pretty fast. This is all about physics in the early stages of impact cratering. So kinetic energy, half times mass velocity squared. And again, it doesn't take much imagination to realize the tremendous energies that are released by these events. So what happens is that the projectile slams into the surface of a planet. It stops moving once it's got down to 1 or 2 times its diameter in depth. And then essentially a shock wave radiates out from the front of the projectile into the target surface. And it's actually the shock wave which compresses the rock and a subsequent release wave that excavates the crater, and not the projectile itself. It's not like when you fire a gun into the sand and the projectile makes a little hole not much bigger than it. A 1 kilometer sized projectile, give or take, will form a so-called transient crater, maybe 10 kilometers across. For small craters, and again, small to me may not mean small to you, below about 4 kilometers or so on Earth, we form a simple bowl-shaped crater. So this is the famous Barringer or meteor crater in Arizona, one of the first, if not the first, to be recognized on Earth. Many of you may have maybe been here on vacation. I would definitely encourage it. It's a mere 40 minutes drive from Flagstaff, so most people go up to the Grand Canyon and miss this really great place. There's a beautiful museum here for scale, and this is a big hole in the ground 1.2 kilometers across. And again, by solar system standards, this is a small impact event that will happen every few tens of thousands of years. What happens when the hole gets bigger, kind of just like digging a hole in the backyard, is that gravity starts to take over and this hole becomes unstable. And essentially 2 things happen. The walls of the crater start to collapse inwards and the floor of the crater uplifts or rebounds. And so this forms something that looks like this. Hope you'll agree with me that this looks nothing like this simple bowl-shaped depression of meteor crater. But what we have here is rocks that are uplifted from depth in the center. We kind of have a depression, which we see here because Hydro-Quebec dammed a couple of big rivers. And in this case, because this is an older structure, the rim of the structure is out here at about 100 kilometers across. Of course, I like to say anyone who studies impact events can't just look at one particular object in the solar system. The Earth is great because we're able to walk outside, drill down many kilometers, kind of walk up to the outcrops. But the Earth is an active planet, and so no crater on Earth, maybe bar meteor crater, kind of preserves its original pristine form. And so this slide, we go to the moon. This shows what happens as you increase the diameter, which basically reflects the increase in energy and therefore projectile size. And so something on the order of 7, if you can't read it from the back, this is 7 kilometers across, 16, 28, and then 320 kilometers across. And so you see this bowl-shaped form starts to collapse inwards. You form this so-called central peak, a mountain in the center, and then at even bigger diameters, this mountain collapses back down to form what we call a peak ring structure. And so that's basically kind of an entire, well, half of my graduate class in kind of, what are we, about 10 minutes. And so I really want to get on to today's topic, which is what I've devoted most of my research in the last few years. It was actually the title of my first NSERC discovery grant back in 2008, which is the beneficial effects of meteorite impacts. Before coming to Western, I actually wrote this New Scientist article and had nothing to do with the title, but I still like showing this. So we're actually maybe getting closer to this now, whereby meteorite impacts after they form are actually beneficial for life on many fronts, and I'll talk about that next. And so probably a decade ago, definitely 20 years ago, if you ask a population of not just the public but scientists about are there any benefits for impacts, well, those in Canada would maybe think of Sudbury, just up the road in the economic resources, and I'll talk about Sudbury later. But what I want to talk about here is the beneficial effects for life. And by life, throughout this talk, think microbial life. Of course, if we were around at the time of impact, they're definitely bad. But for the origin of life on Earth, evolution of life on the early part of Earth's history, think about microbial life when I talk about all of this. So I don't have time to talk about all of these different aspects, but Shantanu mentioned it already. But one of the aspects I've been focusing on is so-called hydrothermal systems. So what are hydrothermal systems? Well, it comes from two Greek words, hydros and thermos, heat plus water. If you think of Yellowstone National Park, Iceland, New Zealand, hot springs, geysers, steam vents, essentially all you need is a heat source plus water. And on Earth today, all of those active systems come in volcanically active regions. So the heat source is magma below the surface of the Earth, and there's water around everywhere. And so really, hydrothermal activity is common. So this is where I actually found myself 2 weeks after landing in New Brunswick, my first time in Canada, kind of down here, more trees than I'd ever seen in my entire life. And then shortly was shipped off to northern Canada, to Devon Island, and this really unique environment. So this is a Landsat satellite image, true color more or less. Tiny little patches of vegetation here, but this is really a polar desert environment. So no vegetation, a really fantastic place for doing geology. And this is where I cut my teeth in looking at meteorite impacts, and still returning. The last trip was 2 years ago. So it really is a beautiful place. This is just taken on a plane coming in, a very Mars or Moon-like environment, which is why we go there, not just because of the science, but to test technologies and things for future exploration missions. So I'd say at heart a field geologist. I got into geology in the first place because I like the outdoors. And so spending a month or two each summer up in the Arctic was really heaven for me when I first came to Canada. So this was home for kind of my first 2 months in Canada, as it were. The rim of the crater is just over this big lip. And I forgot to say earlier, but this structure is about 23 kilometers across. So it's a fairly sizable structure. You're kind of just seeing the other side of it on the horizon as the curvature of the Earth starts to go away from you. So you kind of stand there and wonder about what happened all those millions of years ago. So one of those, I walked into this not knowing anything, and I still didn't know anything when I was in the field. And so this was very much an exploratory field season for me the first time. And of course, as typical discoveries happened in science, this was 2 days before we were due to lead, walking around and saw an incredible outcrop in the south of this structure, where we see what just leapt out to me to be evidence for hydrothermal alteration. And I'll just guide you briefly through this. So there's a rock hammer here for scale. The green and the orange and the yellow are all minerals that were deposited after the impact by these hot fluids that percolated through fractures in the crater floor. The heat source in impact events comes from largely impact melt rock. So the orange unit here, which corresponds to this kind of bright gray unit, are rocks that were molten by the impact event. And so again, because of those high energies, you melt many cubic kilometers of rock in an instant. 2 or 3 seconds to melt maybe 50 cubic kilometers volume of rock. So it's an incredibly energetic process, but that ends up in the center of the crater and is our heat source that drives hydrothermal circulation. So that's just one evidence. Impact. The other thing you need for a hydrothermal system is conduits or pipes for fluids to flow through, and of course, because of the energies, impact events are very good at breaking up and fracturing the surface. And so on the screen here are just some veins, so fractures that are filled by later mineralization. These orange streaks here are kind of not the nicest to look at in the field, but they're the most interesting because that's all of these little red dots around the exterior here. And this is one of the unique things that I was able to do at this structure, was to map out for the first time where in an impact crater these hydrothermal deposits occur. And we'll get on to why that's important in a few slides' time. And so in a paper published a couple of years ago in Icarus, comparing hydrothermal systems on Earth and Mars, this was actually one of my favorite papers to write because I think there were 4 professors and about 5 students from Western on this paper. We put our heads together and came up with this kind of schematic overview of how these hydrothermal systems form in impact craters. And the pitch here was not so much for Earth scientists, but for planetary scientists. Many of you may follow the Mars rover missions, and one of the big things they're looking for is evidence for life. And I'll get onto this in a second too, but hydrothermal systems are some of the top priority areas. So what we wanted to do here is essentially say, okay, if you land a rover here or here or here in an impact crater on Mars, these are your chances, or these are the places to go to look for these hydrothermal deposits. And again, I've kind of hinted at this already. Why the interest in hydrothermal alteration? 2 things: the economic aspects, which I'll get onto at the end of this talk, but also the implications for life. And so this isn't new. Charles Darwin in Origin of Species kind of framed his idea of where life originated on Earth. Of course, we still don't know when exactly or where exactly or how exactly life originated on Earth. It's one of those big questions that biologists and geologists and really any scientists in the room and elsewhere are trying to answer. But the reason we think hydrothermal systems are so important is that this is a really great view of our terrestrial tree of life. So we're kind of way down here on one of the ends of these trees. The root of the tree of life, where some kind of the oldest of our ancestors meet, are color-coded here in red. And that's because, so red is 90 degrees above, orange is 75, and yellow is 60. So it turns out, again, to our knowledge, there's still debates about this, but the oldest forms of life on Earth that we know of are what we call thermophilic, so heat-loving organisms. They only grow at temperatures above 60, 75, or 90 degrees Celsius. And so that's very hot for us. And I mean, the current record breaker from a spring in Yellowstone is 124 degrees. I mean, these are extremophiles. And one of the reasons we're interested in, of course, looking for these hydrothermal habitats on other planets is to go to these sites where life may have, if not originated, colonized and evolved and preserved evidence. Okay, next to the 2, impact glasses. So this will be a short little phrase. This is some work that one of my PhD students, Haley Sapers, is doing. I should say throughout this that I'm only really here today because of my group, and of course all of this research is our research. This particular slide is from Haley. This is one of those other neat things. I think Neil Banerjee is not in the room because he's on travels right now, but Neil and I met 2 years before, actually before we both came to Western. Neil at that time was working on weird tubular structures in volcanic glasses. I showed him an image of a glass from the Ries crater in Germany from my PhD, and Neil said, "Whoa, that looks like the same thing." This then got put on the back burner for 10 years until Haley came along and we co-supervised Haley, and she ended up with a great paper in geology last year where we're essentially comparing features that Neil had seen, which is the top row here, and features that Haley found in these impact glasses. And so Neil and many others have proposed that these tubular structures, you see these beautiful segmented textures, bifurcation, lots of textures that we think can only form from biology, not simple inorganic processes. And so Haley came along and showed that the same textures and structures are found in impact glasses. So a glass is some of that molten material from the impact event. So again, high temperature, high pressure material, but it's thrown all around the surface of the Earth and other planets by these impact events. And so you could literally be seeding planetary objects with glass and other material that I won't even go into from impact events on the early parts of their histories. And so just coming to this is maybe one of the most speculative slides. Along with Haley and Alex, who sat in the room, we're actually working on a bit of a review paper now where we want to put all of this together and look about the origin of life on Earth. And we have some evidence, and we're going to speculate a little bit too. But if we look at the early parts of Earth history, one of the problems with studying the Earth is that we have, well, few to zero rocks left in the first 500 million years of Earth's history. So we call this the Hadean, after the Greek god of the underworld, because the general view is that it was hell on Earth. Asteroids coming in daily, huge volcanic eruptions, so not a very nice place to be. And so it's interesting that we have the first evidence for life at about 3.8 billion years, which is around the time of the end of this so-called late heavy bombardment period, when we know that impact events were 10 to 20 times more likely and abundant than they are today. So there's this question that's been in the back of my mind for over a decade now, which is why, or more, how could life have originated on early Earth if it looked like this? And so what hopefully I've shown you just a sample of in the previous few slides is that even though impact events are devastating for a small regional area around the point of impact, afterwards they may be like the most attractive and beneficial site for life. And so in this paper, we're going to provide a review of the habitats, but also look at potential ingredients for life as well. And I'm not going to get into panspermia and the transfer of life between different planetary objects, but we'll leave that at that. Okay, I have completely no idea how I'm doing for time. So I'm going to go into the second stage of this talk, which is perhaps, well, depends on who you are and what your view is, but the biggest benefit of meteorite impact events, which is the economic deposits associated with them. So I'm sure if I asked to raise your hands, most of you have heard of Sudbury, driven through it. Most of you know that there's a lot of mining in Sudbury. And the two and two do go together because Sudbury is the site of an impact crater anywhere from 200 to 250 kilometers in diameter. So the next time you actually drive through Greater Sudbury, all of the horizon, everything you're seeing in Sudbury and all the way up on Highway 144 to Timmins is actually part of a really ancient impact event that formed about 1.8 billion years ago. Of course, Sudbury is North America's biggest mining camp and powers the Ontario economy. And so this is something that I've got into in more recent years. But it's interesting, besides Sudbury, about a third of all impact craters on Earth actually possess economic deposits of one form or another, which is a pretty high percentage when you think about it. Excuse me a second. And they're very diverse too. We would lump building stone in this, Manicouagan damming for hydroelectric purposes, but we tend to think more of mineral deposits, and there's three different groups. Progenetic, so you can kind of think of that as more pre-impact, syngenetic, formed during the impact, and then epi, kind of post-impact. And so I'm just going to talk about Sudbury today because I've got quite a bit of research going on with other folks in the Department of Earth Sciences. But as an example, uranium, one of the biggest uranium mines in Western Canada, the Carswell, well, it's in the Carswell impact structure, comes from basically uplifting uranium deposits that were 10 kilometers down before the impact and bringing them to the surface and then kind of super concentrating them through hydrothermal alteration. Diamonds. This was actually Bob Lennon who told me the world's, I'm not sure if this would technically be the correct, but the largest single deposit of diamonds in the world is not from a kimberlite pipe, it's in an impact crater in Siberia, the Popogai impact structure. The problem is in Siberia, and they're all nano diamonds. So there's lots of them, but they're finely dispersed throughout 100-kilometer diameter impact craters. So it's not economic to mine, but basically you form diamond because you compress coal and other carbon-bearing sedimentary rocks. Another surprising one, there are actually 4 or 5 impact craters in Alberta and Saskatchewan where we get lots of oil and gas out of. One of the reasons there is that you have they're perfect for exploration. It's a bullseye, a circular structure, lots of fractured rock, and essentially they form ideal traps. As you can maybe imagine, oil and gas can migrate into here and form ideal traps for oil and gas. For the petroleum geologist at the back there, he probably knows this, but one of the most prolific oil wells is from granite. Which if you've ever taken petroleum geology, we don't typically think of granite as a good reservoir rock. And it's because in the center of an impact crater in North Dakota, I believe, you've broken up granite in the center here and it's been just pervaded by oil and gas. So the list is quite long, lots of different deposits, but today I'm going to talk to you about the Sudbury structure, which is of course close to home and is important for the economy here in Canada. So this is a digital elevation model of Sudbury. If you look at Google Earth, it really isn't obvious. You can see, we call this the North Range. So Greater Sudbury is down around here. You would drive up on a Trans-Canada, kind of come in here. Highway 144 that many of you might know of kind of goes up into Northern Ontario, comes through here. And if you've ever driven on that road, you do go uphill a little bit. But this basin here, so green is low, blue is even lower, and red is high. This is 60 kilometers by 30. So this is a tiny remnant of something that was really kind of this big initially, at least 200 kilometers, if not even bigger in diameter. So very quickly, a kind of schematic geological map. So hopefully you can picture this kind of range here is this here. And so we call this the Sudbury Basin, and it's lined by this pink unit here. So at Sudbury, because it was such a large impact crater, we formed something called the Sudbury Igneous Complex. It used to be called the Sudbury Eruptive. It's 3 kilometers thick. So stand here, look up 3 kilometers, 3,000 meters. That's the amount of rock that was melted by that impact event. And that was spread out over easily 100 kilometers across. So an enormous hydrothermal system was actually generated here. But we'll get to the ore deposits in a second. So Sudbury is kind of unique and unusual. It formed at the junction of 2 geological provinces, and now today a third one, the Grenville province. I first went to Sudbury as a grad student and then taught field school. The Earth Sciences Department runs a field school about here in Whitefish Falls and has done for about 40 years or so. Really still kind of within the regional effects of this large impact event. So this is something we call the Southern Province, and then the Superior Province is up here. These are really old 3-billion-year-old rocks typical of the Canadian Shield. Very complicated diagram, but basically to say that, okay, no one's shot their hand up to say, hey, this doesn't look like an impact crater, so I should say something very briefly now about this. Sudbury is not circular. It is 1.85 billion years old. It's been deformed by, we think, at least 3, if not 4 major orogenic events. And so it's a very complicated place to work, which is why there's still kind of scope for me and others to come in 100 years after they've been mining Sudbury to come and piece together some of these puzzles. So there are 4 main types of deposits at Sudbury. So this essentially is a simple cross-section going, let's say, from north to south. The pink here are these rocks that were melted by the impact event. You'll notice most of the ore deposits occur what we call in the footwall, at the contact, at the base of that, and then disseminated out into this into the ground beneath the impact crater. This is a rock hammer for scale. Why is Sudbury so important? Well, I mean, this is 100% sulfide. Some of the veins at Sudbury, they typically drive shafts a few meters across, and the veins are wider than the shafts. So, I mean, it's an incredibly prolific mining camp because of how concentrated the ores are there. But despite 100 years of mining, there's still quite a few questions remaining about how many of the ore deposits get there. And so one of the ones that we're tackling in partnership with a couple of mining companies are these so-called offset dike deposits. And so the pink here is this interior previously molten material. And you'll see that there are dikes, so fractures filled with melt that extend out kind of radially and concentrically. And so my group is tackling, well, the mining company, of course, wants to answer the question, help us find more ore deposits to mine. Before we can do that, though, we've got to answer the question, well, how did the ores get to where they are now? And actually, until we can answer that question, how on earth did these fractures form, and when in the cratering process did they form? So there's some really big picture questions, and in fact, I've given presentations pretty much on planetary geology to a lot of the mining companies, and they kind of lapped it up. Because we're taking a step back and thinking about how does this, Sudbury didn't look like this 1.85 billion years ago. It either looks like this or this. 2 big craters on the moon. If we can figure this out, then we can maybe start to predict where we are in the structure today. For example, you can take an envelope, back of a piece of paper, and you can draw the Sudbury Basin kind of anywhere in here. You can squish it from any direction and make the current orientation of Sudbury. And so we really don't know. And so that's one of the big things we're doing. And how we're tackling that? Well, a lot of time spent in the field. This is actually, we've been trying some, this is a trench that was cleared, student here and here for scale. And there's actually an image from a balloon. We're trying to get a good, cheap air photograph of the outcrop, and it turned out pretty well. Hopefully, even from the back of the room, you can see this offset dike material is gray, and it has lots of pieces, fragments of rocks from before the impact that were broken up, incorporated, and sent all the way through. And if you were to look at this close-up, you'd see sulfides, metal-bearing minerals scattered throughout this rock. So many of my students are doing detailed mapping. They're kind of mapping, I think we made the cutoff at 50 centimeters. I didn't make them count anything smaller, but we're collecting a lot of field evidence. We're combining that with a lot of geochemical data using sophisticated software. And so this scale here, this is 50 meters. So this is essentially a map in a program called IOGAS, where we can plot on the geolocation using GPS coordinates, and then plot out the different types of rocks, and then we can do take it on instruments like the electron microprobe that we have over in Western Science that Bob Linden and I received funding for CFI, and look at them on a very fine scale. So we're kind of going from essentially satellite image down to the outcrop scale, down to a thin section, and now down to 200 microns. And so finishing up very shortly, I think, this is a picture of a pyrite crystal, about what, 3/4 of a millimeter across. This is pyrite, fool's gold, of course. This is not particularly interesting for the mining companies. But what is when we start to see features like this. And so one of the unique capabilities we have on this microprobe over the road is to take a particular element, in this case cobalt, and scan this single crystal for a few hours and get an idea of the distribution. And so what you're seeing here are essentially growth crystals. Remember back in either chemistry today or when you were a kid kind of growing copper sulfate crystals and you can watch them grow. Well, here we obviously have maybe 3 different domains, something in the core here, something here that's quite rich in cobalt, and then this outer rim that is quite poor in cobalt. Why is this interesting? Well, there's a big debate at Sudbury as to whether most of the sulfide minerals formed magmatically, so whether they crystallized out of that impact melt deposit, or whether they were formed from the hydrothermal system after the impact event. They probably formed from both, and this we actually are thinking is a magmatic pyrite, and this is a later hydrothermal event. But you can see very fine textures that we can look at here with the instrumentation we have on campus. And so just to kind of wrap up, again, I wrote an NSERC CRD with one of these companies, and actually, despite this being a Canadian mining company working in Sudbury, they were quite happy for us to do some research looking at Mars and mapping impact craters on Mars. And you may be thinking, why? Well, again, one of the problems is that Sudbury is very eroded, very old, and lots of trees. So we can go to the Arctic, but we don't have a good large example up there. But we do, when we look at Mars and other planets, a really amazing high resolution. And so I think, again, Shantanu Agarhad mentioned this. My research scientist, Livio Tornabene, who many of you may have met, works on something called a HiRISE camera on the Mars Reconnaissance Orbiter. This is essentially a whopping great huge camera. The lens is something like this big, and it takes pictures of Mars that return images at a 25 centimeter per pixel resolution. So we can image that table on the surface of Mars, and the best thing for us is that they're free. So we have satellite data like that on Earth, although the military bars it from being anything below, I think, 30 centimeters a pixel, but it's very expensive. But here on Mars, we have lots of free high-resolution data, and you might have to come up at the end to see this. This is 30 meters across here. And lo and behold, we have dikes of material that are running through the structure. And if you've got really good eyes at the front, hopefully people agree with me, there are little fragments and clasts of rock caught up in these dikes. And not only that, but they're offset as well. So these are actually perfect analogies for the so-called offset dikes at Sudbury. And so if we can map them, understand how they're formed on Mars, bring that back to Earth, then it might kind of, through a very circuitous route, help find more ore deposits at Sudbury, which I just find pretty cool. And so, in summary, hopefully what I've shown you today, impact cratering, I think most of the new textbooks kind of do talk about impact cratering being an important geological process, but this wasn't the case when I did my undergrad. I know we never really heard about meteorite impacts. Many of you are probably aware of kind of the negative effects, and this debate is still ongoing, but there's at least one mass extinction event that is at least partially associated with the impact of an asteroid or comet. But this is what I've been focusing on in my research group, kind of the beneficial effects for life and for economic deposits. And so I do want to say quite a few thanks. I won't bore you too long, but I did want to take this opportunity to acknowledge a lot of funding from various federal agencies and companies in Canada. I wanted to, especially those of them like NSERC and the Northern Scientific Training Program that take me and my students to amazing places like this in the Canadian Arctic. I want to thank all of these faculty members who I've co-supervised graduate students and postdocs with, and I hope this list grows. I really enjoy collaborating and putting different heads together to solve interesting problems. I'd like to thank the departments in particular. They took a bit of a and the faculty a bit of a leap of faith in hiring me on a 3-year fellowship as a limited term appointment in 2007. And so, yeah, take more leaps of faith in the future, please. Everyone in the departments and the faculty, all the admin staff, all the staff throughout those 2 departments have been fantastic. Of course, the CPSX team, the Center for Planetary Science and Exploration, and in fact, Peter is in the room, and I have Peter in particular, I think, to thank for helping convince the departments in the first place to bring me here to Western. And my team, spacerocks.ca is our website. And again, I wouldn't be here without all of the research that my students are doing. And some of them received Ontario graduate scholarships today, so I'm thankful for having such a wonderful team of students. And then someone who gets the biggest thanks for putting up for me for quite a few years, my wife Laura Meisner, who's a faculty member in another faculty here on campus, in the Department of Kinesiology, for putting up for me for, I think, 11 years now. So I'll say thank you, and I think I can take some questions.